Okay, here we are again. We're going to start with section 1.6 in just a moment. Real quick, I want to say a few things. First of all, about the homework. Last week I sent an email detailing all the particulars of homework 1 that was due on that Sunday. This week I'm not going to do that, right? So, I mean, in general, it's all on the class schedule, and so it's part of your job is to keep up to speed and make sure that you're aware of all those homework due dates. And so I'm just making a class announcement today, and next week I'm not going to make any announcements at all, right? It's just going to be all automatic at that point. Okay. While I'm at it, let me also point out with homework 1, there were a few cases of students who didn't associate pages to the submissions. This is actually really important. We wrote it down somewhere. I think it was on the exams and homeworks page, something like that. But it is part of a homework submission. So if you didn't associate pages, technically you didn't submit your assignment, right? So you have to do the page associations. Now, on the faculty side of things, I can't see what the student side looks like, so I actually don't know how to do it, right? But I hope it's something that y'all can figure out. If you can't figure it out, and if you can't get a friend or OIT or whatever to help you, bring your stuff on into office hours and we can sit down and I'll help you figure it out, right? One way or another, this is doable. But again, reminder, it is a required part of a homework submission. You have to do that. It's an important part of how we keep the homework grading efficient. Okay. So second announcement is about attendance. So I have not been checking attendance up to now, right? As I mentioned on the first day of class, we'd start that, later once the roster was settled. I think the roster is pretty settled at this point. So I will need to have time to get everything together to be able to make sure that the system's in place and everything. I'm going to have to create a Canvas site. I've got to create my attendance quizzes and all of this kind of stuff. And it adds up. It takes several hours to do all that. I may or may not be able to do that in time for Monday. I'm kind of betting against. I'm guessing at this point that Wednesday will be our first day where we will actually take attendance. But anyway, I will send an announcement when everything's set up and ready. And what I want y'all to do, aside from, making sure that you're aware that yes, indeed, we are going to start checking attendance pretty soon here. Make sure you go back and reread all of the stuff about the rules, right? There's various rules and procedures. So, for example, imagine that the Canvas app on your phone is probably the easiest way to make your submissions, right? Rather than a laptop. But suit yourself. I have no position on how you do it. But what I do have a position on is you have to note your attendance by successfully answering the attendance quiz on Canvas while the attendance quiz is available on Canvas. That's the only way to get credit for attendance. And various other blah, blah, blah details. Again, make sure to read all that stuff soon. Okay, back into the math. So, 1.6 is mostly stuff that y'all have seen before. It's mostly linear algebra. So this is kind of most of it right there. Just right. Make sure to reread. A lot of it's going to look familiar, but make sure you're good with that. A couple of things that are worth talking about. I mean, I'm not going to talk through the triangle inequality here, but I thought it was worth writing down. This one I am going to talk about a little bit. I think this is underappreciated. I think this is a fabulous way to think about multiplying a matrix times a vector, and it's not the formula that most people see first. Most people see the formula for matrix vector multiplication where you do kind of dot products with the rows. And you compute the coordinates of the product, sort of one coordinate at a time, but dot products with the rows of the matrix. That's not what this is saying. Right? This is giving you a different point of view on how to think about a matrix vector product. Now, from a computational standpoint, this is probably not as good. Let me also remind you, that's not particularly important to what we do in this class, right? Computation is it's a necessary you got to do it. But that's not really the main thing we're interested in. The main thing we're interested in is how do these ideas relate to those other ideas and stuff like that. So let's talk about what this one is saying. And I'm going to try to persuade you this is ultimately the better way to think about matrix vector products. What this is saying is that a matrix vector product is, and you can see right here, it is a linear combination. Linear combination of what? Well, it's a linear combination of the columns of the matrix. It's literally a linear combination of the columns of the matrix. Right there, I'm already kind of sold that this is a really interesting way to think about a matrix vector product. It's a linear combination of the columns. You're telling me that a matrix vector product is always in the span of the columns? It's literally a linear combination of the columns? Wild, right? That's geometrically interesting. Geometrically natural. Right? So already, that's kind of neato. But not only is it a linear combination of the columns, I can tell you what the coefficients are. The coefficients that you use are the coordinates of the vector that you're multiplying by the matrix. So really nice, really simple, really ultimately pretty natural, right? And I am constantly kind of amazed that this is as undersold and underappreciated as I feel like it is. So I wanted to make sure that y'all saw it. Notice again, this is all exceptions granted, different points of view, different kinds of situations, and I think in most cases this is the one that most directly connects this new construction to existing ideas. So I think it's the best point of view on matrix vector multiplication. All right. Okay. Linearity. So I have this in here because Math 353 instructors, I have gathered on several occasions that they feel like students come into Math 353, which I think most of y'all are going to be taking eventually, right? Probably next semester. Math 353 instructors very often feel like their students seem not to know what linear means, right? Now, of course, y'all have taken an entire course called linear algebra, right? And ultimately, the word linear is why they call it linear algebra, arguably. And so it's a really big deal. It's very important to know this. Linear means that right there. It just, different ways to say, how to interpret, how would we enunciate this in English? One way to say it is that if you do a linear combination before you plug in to the transformation versus doing that same linear combination after you've plugged into the transformation, that you get the same thing either way. A function that has that property is, that's a little bit of a surprising property. It's certainly not true for most functions, right? But this is a special property, kind of a natural special property that a function can have. And so it's worthy of a name, so linearity. Okay. All right, so make sure you're comfortable with that. By the way, to be clear, we're going to spend most of our time in this class talking about Euclidean linear transformations, by which I mean the domain is a Euclidean vector space and the target is a Euclidean vector space. So Rn and Rm, something like that. It could be any vector spaces, but and I think we're going to have one instance in this class where we actually will talk about a non-Euclidean linear transformation. Great majority is going to be Euclidean. All right, now real quick, and you'll notice I'm in the, y'all are going to read most of this section, so do take that time. I will point out, we've already kind of done this example here. We talked about how last time when we were talking about cross products, and I made the statement that, in a sense, you could say it as that cross products are linear. Asterisk, yeah, it's a kind of an abuse of the term. When I say cross products are linear, what I really mean is that if I fix some vector A, and if I think of a function which is just always cross product with A, whatever x you give me, we're going to cross it with A. Crossing with A is what we do, right? That function is linear, right? So we talked about that last time. So a little bit of an abuse to say cross products are linear because it's not really the full cross product. I have to sort of say I'm thinking of just, in some sense, just the right side input into the cross product. That's the only thing that's actually the variable. And the left side input, I have to say, well, I'm assuming that that's fixed, constant. But nevertheless, people will say cross products are linear, and this is what they mean. All right. So a related, by the way, likewise, dot products are linear, and again, equivalently, interpreted. This third example is a little weird. You may have seen something like this in Math219. Again, there's something in play here that's linear. I'm going to talk about this function called D. The very first thing you might think when you see this is that D is determinant. That is absolutely not true. D is not determinant. And by the way, determinant is not linear. It is really not linear, right? If you multiply a matrix times 3, the determinant does not just multiply by 3, right? It's really not linear. So D and determinant are different things. Let's be clear about how this works. D acts on only a single vector, x. And now what is it that D does to x? Well, you'll see I've put x right there. What D does is all of the rest of this. All of that. That's what D does. D says, oh, you're going to give me a vector x? Okay, all right, I'm going to make that my bottom row of a matrix I'm going to construct. All the other rows I'm going to fill in with a given fixed list of vectors that are just constants as far as we're concerned. That will then generate an entire matrix of which I take determinant. Right? So this function called D is linear. You might say one vector at a time, like one row at a time. If you think of everything else as fixed, one row at a time, it's, the determinant with the understanding that you're not changing most of the matrix, you're only changing one row at a time. That thing there is linear. And casually speaking, people will say determinant is linear in its last row. Right? And this is what people mean when they say determinant is linear in its last row. Side note, determinant is also linear in every row. Side note, it is also linear in every column. Right? All together, all of these properties together, all of these sort of one row or column at a time linearities, is called multilinearity. It's a really, really cool property of determinant. I'm not sure if y'all heard that term. Real quick show of hands, multilinearity. Anybody heard the term? Well, of very few. Okay, all right. So I guess that's not used in 218, but it's pretty cool. Okay, all right. And now a really important theorem. This is, as far as Math219 is concerned, I think this is arguably one of our, let me not overstate it, this is certainly one of the most important theorems to Math219 that we will borrow from linear algebra. Right? So in terms of this course, this is one of the absolute biggest ones. And loosely speaking, it just says that every linear transformation is a matrix. And pretty much. Now again, the understanding, we're only talking about Euclidean linear transformations. And we're also, when I say is a matrix, what we mean is represented by a matrix in this way. the usual way. You give me a matrix, this construction right here makes a function. And I'm saying whatever linear transformation T you give me, there is a matrix that makes that linear transformation. All right, so I encourage y'all to read the proof of this. It's a pretty straight read. If you get stuck on any of this proof here, come on into office hours and let's talk about it. I'll be very happy to help you wherever you might happen to get stuck. You can see it's not particularly heavy machinery or involved or heavy algebra or anything, right? What I am going to point out here, and this is a really big deal, is that not only does this proof show us that there is such a matrix, but this matrix, the matrix that represents whatever linear transformation you're interested in, I've got an explicit formula for it right there. And make sure to know that formula. Super important, right? Really, really, really important to know that formula. And let's focus in on that formula and think about it for a minute here. So what is this saying? What this is saying is if you want to represent the matrix, and again, here's the formula, the columns of that matrix, I'm going to tell you what the matrix is one column at a time, right? The columns, here they are. The columns are what you get by applying the linear transformation you're interested in to the standard basis vectors. That's all it is. And the way I like to enunciate this is to say the columns are the images. Keep in mind the term images. That just means what comes out, right? The columns are the images of the standard basis vectors. This is one of the most important little pithy phrases to make sure that you are just extremely comfortable with. And I'm going to show you a quick example, at least the big picture of the quick example, how to apply this. I'm going to come over here to the side. We've got some space. Okay. Let's talk about a rotation. If I want to rotate counterclockwise around the origin by some angle theta, how would I write down a formula for that rotation? And it's not necessarily by some convenient angle. If it was always pi over 2, that'd be easy, right? But by an arbitrary angle theta, how do I rotate an arbitrary vector x by an arbitrary angle theta? So, sequence of observations. First of all, it's a linear transformation. It's a good one to think through for yourselves. Try to persuade yourself that this is, I think, pretty clearly a linear transformation. But again, think it through, right? Secondly, every linear transformation is a matrix. Thirdly, here's the formula for the matrix. Apparently, all I've got to do is take the standard basis vectors, E1 and E2, do the linear transformation to them. So I'm going to rotate them by whatever the given angle is. Whatever I get, those will be the columns of my matrix. Simple as that. So you can see there's a little bit of trig involved here. If I take the E1 vector and rotate it, well, this right here is this is my angle, whatever the angle for the rotation is, and this magnitude is 1 because it came from this, which has magnitude 1, and right triangle and trig, and you can just do the appropriate trig, and you can straight up solve for that first image of the first standard basis vector, which is going to give you your first column. Everybody see what I'm talking about there? And then likewise, Whatever you get when you take your second standard basis vector and rotate it, that's going to give you your second column. Throw it all together, and there you go. And I'll go ahead and write down what the final answer is so you'll know what you're aiming for. What you're going to end up with is the matrix is cosine theta, sine theta in the first column, and minus sine theta, cosine theta in the second column. So I think it'd be a really, really good exercise. I urge everybody to take a little time to make sure you can do this. Use this strategy right here. Work out the details. Make sure that you get this as your final answer. Is that cool? All right. Okay. There we go. I don't know what happened there. There we go.
Is it the second column? Is it sine minus sine and then cos, or sine and then minus cos?
No, it's minus sine and then cosine. Yeah, pretty sure. Yeah,
because you said it's the second vector. The second vector.
Yep.
After we transformed it.
That's right. If you take let's see here. So this vector right here. Right, and you think about what are its x and y coordinates. Well, the x coordinate here, how does that x coordinate relate to the trigonometry of this angle theta? Yeah. And by the way, real quick comment as well. I do think triangles serve a purpose in thinking about trigonometry, and you could take a triangle's point of view on this. I do want to make sure everybody is aware of and comfortable with that. Really, trig is much better defined with the unit circle. Right? Triangles are a very limited way of thinking about trig. Triangles only really make sense for small angles. Less than pi. Right? It gets a little sort of like, is that even really a triangle? If there's an angle of 9 pi, what would that, as a triangle, what does that even look like? It gets weird, right? But the unit circle, no problem. So something to keep in mind. Make sure you're good with that unit circle point of view. Okay. All right. Okay, another real quick thing to read. I kind of like making a quick comment about this, though, and that is that the formula for matrix multiplication is super weird. When I first saw that formula for matrix multiplication, I thought, you got to be kidding me. This is supposed to mean something? Somebody made this up. Somebody, and then a row with a column. Come on, now you're just being weird on purpose, right? I couldn't make any sense out of why that would be the formula. And I didn't understand until quite a bit later that, no, there's a really good reason for that formula. That is not pulled out of thin air. That is what the formula has to be to have matrix multiplication correspond in the usual way of how linear transformations relate to matrices, to have matrix multiplication correspond to composition. Right? So, matrix multiplication is just a kind of a matrix version of composing linear transformations. And composition is an extremely natural construction. What comes out of one function, you stick it into the next function, right? That's very natural. So matrix multiplication is what makes that work from the point of view of matrices. Yes?
Between the S and the T, the dot product?
No, this means composition.
Okay.
Yeah, it's a little circle. Yeah, and I hear where you're coming from. But yeah, a dot product, you have to make it a dot. It doesn't have an inside. This is a little tiny little circle. Yeah, right. Okay, so that's 1.6. Moving along, we're going to talk about different coordinate systems. I think y'all are already familiar with rectangular coordinates. Well, of course you are. Just be aware there are certain things about rectangular coordinates that are very, very convenient, but that we can't take for granted. because they're not going to apply to other coordinate systems, right? So unfortunately, the fact that rectangular coordinates are unique, not so for any of the other coordinate systems we're going to use. So we're going to have non-unique coordinates, and I'll show you some examples in a second. Rectangular coordinates have these, I'm going to say, play nice with linear combinations in the sense that, for example, if you want to write a vector as a linear combination of standard basis vectors, the coordinates are the coefficients, right? That's nice. You got to love it. That's a peculiarity of rectangular coordinates. It does not work in any other coordinate system we're going to do in this course. And then likewise, this cool linear combinations formula, if you want to do a linear combination of vectors, you can do it one coordinate at a time. It was really nice. That's an oddity of rectangular coordinates. So don't take too much for granted. We have to recognize what is, in fact, peculiar to rectangular specifically. Okay, so moving along, let's talk about polar coordinates. Y'all may have seen this previously. Pretty much that's what polar coordinates looks like. If you've seen it before, great. If you haven't, no problem. Roughly speaking, the idea here, if I can get this to cooperate, let's do it like this. The idea is theta tells me how far to rotate counterclockwise from the positive part of the x-axis. That'll define a direction. And then, loosely speaking, asterisk, I'm going to come back and fix this in a second. Loosely speaking, R says how far do you go in that direction, and then that defines a point. Is that cool? Okay, so why did I have to put an asterisk on that? This is subtle and often overlooked. But how far suggests a distance. Distances are intrinsically positive. There's no such thing as a negative distance. But the coordinate R does not have to be positive. R is absolutely for sure allowed to be negative. Totally fine. R is allowed to be negative. Right? So, here and there, it is very convenient to think of it as a distance because I don't know, it's just the most geometrically relatable thing that we can talk about that it kind of connects to. But you do have to make sure to remember that it isn't technically that. So here's a different way to think about it. You can think of theta as defining not just a direction, but you can think of theta as defining what you might call an R-axis. And then there's where R equals 0, and maybe there's where R is 1, and there's where R is 2, maybe there's where R is 3. And it's like you got a little tilted number line there. And, number lines go the other way as well. -1 there, -2 there, etc. Right? So you could totally have negative values of R. Negative values of R just mean go the other way from the direction that theta says to point. Yeah?
Does that mean R theta equals -R theta plus I?
Yeah, I'm going to get to that in just a minute. Yep. But short answer, yes. Yeah. Right. So anyway, make sure for the moment, just make sure to remember R is allowed to be negative, does not have to be positive, and therefore it's not necessarily a distance. It's a coordinate, not a distance. Let me remind you, I'm sure y'all are previously familiar with the idea of X. The X coordinate. Nothing spooky about that. If X is positive, it represents a distance. It's the distance from the Y-axis. But it doesn't have to be positive. X can also be negative. Nothing creepy about any of that, right? Same thing for R. Okay. All right. Okay, a little bit of trig will persuade you that, I'm sorry, I got ahead of myself. Sorry. Okay, so this is the way we typically think about polar coordinates, kind of, geometrically. I want to plant a thought in your head that you can think of polar coordinates as a function, specifically that R and theta are kind of the inputs. to a function, and that x and y for a given, whatever that output is, the given r and theta, x and y are the corresponding outputs. So r and theta go in, x and y come out. That makes it a function. Why would I want to think of it as a function? Not clear just for the moment, but we will find pretty soon that there's a really good reason that we want to think of it as a function. There's an integration technique that we're going to talk about sort of halfway through the course, for which this is going to be essential. So planting the thought now. Okay, and anyway, the formula for that function, in other words, how do you convert, given an r and theta, how do you find the corresponding x and y? Not hard to persuade yourself. Just a little bit of trig. I encourage you to make sure that you can think that through. But it's mostly, pretty much, just the trigonometry of this triangle right there. Just sort of write down sines and cosines concerning that triangle, and this pops out. Okay, lots of little details to talk about. And again, tough choices. And again, we have a lot of content to cover. I think when we get to the end of the course, you're going to look back on polar coordinates and think, well, I'm glad we didn't spend too much time on that because we really need the time for this other stuff we're doing now in Chapter 7. So I'm going to go a little bit quickly through this stuff. Again, this is going to pay off. Quick observation about the lack of uniqueness. So polar coordinates are not unique. This is your point. If you add 2 pi to the angle, you're just doing a full turn. Of course, it gets you back right where you had been. So add 2 pi as much as you want. Right? Any integer number of 2 pi's, all good. Doesn't change anything. Okay. Here's a variation. If you added just pi to your angle, what does that do? Well, if you add just pi, that gets you going what you might call exactly the wrong direction. It doesn't bring you back to the same direction. It gets you going exactly the wrong direction. But notice, if you then also negate r, and again, it gets you right back to where you had been. Right, so that's another sort of way to come up with a different polar coordinate for a given point. So, So this point in the xy plane, that single point in the xy plane, that is a set of polar coordinates for it, and so is that, and so is that. And you can probably see this coming. So is that, and so is that, and there's sort of infinitely many just as good polar coordinates kind of along in here, and another infinitely many just as good polar coordinates kind of along in there. Okay, does that make sense? Yeah. Okay, next little quickie. Try to avoid ambiguities. I claim it's not clear what this means. 2 comma pi over 6. What is that? Is that r and theta? Pi over 6 kind of looks like an angle. Kind of feels like maybe that ought to be r and theta. But it doesn't have to be, right? Maybe it's r and theta. It could be x and y, though. Pi over 6 is a perfectly legitimate number. It absolutely could be y. So I claim that this is ambiguous. You just write down 2 comma pi over 6. You could mean this point because you were talking polar coordinates, or it could mean this point because you were talking rectangular coordinates. The notation doesn't indicate. So try to avoid these kind of ambiguities, and by the way, also be on the lookout for these kind of ambiguities. The easy way to avoid the ambiguity is just go ahead and say r comma theta equals. Now it's clearly polar coordinates. Problem solved. Right? So, something to keep in mind. Here's a subtler, arguably more dangerous one. Pretty easy to persuade yourself of these formulas, right? By the way, this is a good exercise. Make sure you can persuade yourselves of these formulas. With the asterisk, this one here doesn't work when x is 0, right? So kind of annoying. Whatever. Here's the dangerous part. What a lot of students will do is they'll get to this equation right here and they'll say, and I'm going to write this in red, they'll say, okay, well that means that r is the square root of x squared plus y squared. And that's not true. Subtle, but again, notice what this is saying. This is saying r is positive, which it doesn't have to be. Right? Keep in mind, this symbol right here, a lot of people misunderstand. A lot of people think this symbol means all of the square roots. Or that it means whichever square root is appropriate under the circumstances. Or something like that. Right? And it doesn't. That's not what that symbol means. This symbol means the non-negative, let's just say positive, because this is the positive square root. That's what that symbol means. Right? So you cannot just go around assuming that r must be positive. It is under no such obligation. So this formula is wrong, and I'm going to cross it out. Make sure we're clear on that. And by the way, likewise over here, a lot of students feel an urge to solve for theta and write arctan of y over x. And again, wrong. Absolutely not. Arctan is only allowed to take certain values, right? You say arctan. Arctan will always produce a value that's somewhere between negative pi over 2 and pi over 2. Those are the only values that arctan is allowed to take. Theta is allowed to be any value, right? So also just wrong, just straight up wrong. Now, you might be tempted to think, okay, well, mathematicians get real fussy about these kinds of things, right? So let me just show you how wrong these formulas can be, but furthermore, how wrong they can be in a seemingly harmless situation, right? So let's look at this point right here, negative, that's not the color I wanted. -1, -1. Real easy little point. I'm not doing anything super abstract and weird, right? That's just -1, -1. Nothing creepy. If you take that point and plug it into there and see what these formulas that I've already crossed out. In fact, let's see here. Let me go back to the pencil. If you take these formulas, you will get that r is the square root of 2 and that theta is pi over 4. And that'll put you right here, which is wrong. You see how they crashed and burned on an easy little point? So I think this is a real problem, right? I mean, you got to watch out for these formulas that I have crossed out in red. They are not true, and you cannot trust them. They will make your bridge fall down. Right? This is not abstract. Annoyance or something. This is straight up, full on, wrong answer. Catastrophe. Okay, so keep that in mind. Proper way to do a problem like this. Again, ignore those crossed out formulas. Realize that these formulas here give you options, right? We have all of these, we have 2 different possible values of r, and then we have all of these, quite a few, you might say infinitely many different values of theta. Let me observe. The 2 pi's are kind of boring, right? You can always add 2 pi. It always gets you back to the same point. I kind of don't care about the 2 pi's. Let's forget about the 2 pi's. It is still the case that we have 2 different values of r and 2 different values of theta. And how do you decide which of those 4 possible combinations actually work? Well, you have to actually think it through, right? So, for example, you might just arbitrarily decide, okay, I'm going to look at theta is pi over 4. All right, well, theta is pi over 4 goes that way. For that value of theta, in other words, as I go in this direction, what coordinate r would get me to this point? And you see, well, if this is the positive r direction, apparently I'm going to need the negative r. And so r would be negative square root of 2. Everybody see what happened there? You gotta actively think about the geometry. Don't rely on formulas. Think about the geometry and make sure that you choose appropriately. And not randomly, right? And not based on nonsensical, false algebraic formulas. All right. Okay. That's sometimes you want to convert an equation that comes to you in polar coordinates, and you want to convert it instead into rectangular coordinates. And there's various different circumstances that are susceptible to various different tools. You'll notice what I did here is I squared both sides of the equation and then capitalized on the fact that I already know this formula. R squared is x squared plus y squared. And then the punchline is exactly what I wanted. I have a rectangular equation, in this case for a circle. Different tricks for different circumstances. Here I take tangent of both sides. Why? Well, because I was kind of thinking strategically, and I knew I had this formula, and that's a good way to make theta go away. Is that cool? Everybody happy with that? All right. Sometimes you don't get so lucky. If you try to play those games with this equation, you're going to crash and burn. It just doesn't work, right? But you can still kind of point plot. So rather than pick one angle at a time, I'm going to do this sort of a range of angles at a time. So we're going to start off by thinking about angles like this, from 0 to pi over 2. Well, what does r do for those values of theta? Well, theta is not what goes into sine. 2 theta is what goes into sine. And so the thing that goes into sine, since it ranges from 0 to pi, the values of sine do like this. They start at 0, they go up to 1, and then they come back down to 0, and that has the effect of giving us something kind of like this. So as the green angles vary as we presumed, those purple R's take us around a loop, kind of like that. Everybody see that? So it's a different way of thinking. You know, what y'all are accustomed to with point plotting is that the input goes this way and the output goes that way. And that's rectangular coordinates. You got to kind of, loosen up your mind a little bit and get a little bit more flexible and think about the angle as being the input, and then for a given angle, the radial coordinate being the output. Right? It's definitely a little bit different. Okay. So now what I've done here is I've talked you through sort of the first quadrant, right? Plotting that equation in the first quadrant. I want to encourage y'all to do the second, third, and fourth quadrants. Kind of mimic what I did here. It gets a little strange. One thing you'll notice in particular is that for the second quadrant, for those values of theta, the argument in blue there, 2 theta, goes from pi to 2 pi. And notice then that all of these values of r are negative, which means that, well, because they're negative, we're actually going this way. And that's why it looks like we're in the fourth quadrant. We're actually looking at second quadrant angles, and they just show up in the fourth quadrant on the page because the r's are negative. So details to think through, and then keep going around. when you're done with the whole thing, what you'll find is that this makes kind of a 4-leaf clover. It's kind of cool. Yeah.
Are we in any way supposed to know like how our sine to theta is supposed to draw out?
How what now?
Like if you were to give me r equals sine to theta, like I'm like not able to plot that myself without the help of a computer.
You mean like just with theta like this and r like that rectangularly, in other words?
No, just in that plot in XY, like how you were able to draw out in a pedal shape, you know, like.
Oh well, yeah, no, absolutely. So let me talk about that a little bit more then. So let's talk about for these first few angles, so as wrong. Let's see here. So for these angles between there and there, right? These are the values that R is going to do. R is going to start at 0, and then it's going to do like so, and it goes back down to 0, right? That's just coming from this formula here. Is that cool?
Yeah, I know,
right.
Like it increases and then decreases.
Yeah.
But how much it increases and how much it decreases.
Oh, I mean, you do your best, right? I'm not saying that this is exactly, right? But qualitatively, as my angle increases, I go further out, and it just kind of has to do something kind of like that, right? What else could it do? Does that make sense? In other words, so smaller angles, shorter distance. As the angle increases, I go farther, right? Eventually, I'm going to get to 45 degrees. That's the farthest that I go. After 45 degrees, then I go not as far. That means I kind of have to come back in. I mean, it's just kind of qualitatively going to have to be approximately like that. It doesn't need to be perfect. Does that make sense though?
Yeah.
Yeah. Okay. That's all we need. Yeah. You scared me for a second there. I thought you were telling me you didn't know what sine waves were. Yeah. Okay. Yeah. Okay. Alrighty. Moving along. Couple other little, tricks, right? Good to have seen examples of. The little trick on this first one here, little subtlety, you see this R, you think, ooh, I don't like R, but I love R squared. How about I square both sides of the equation so that I can play this game? And that's the wrong move in this case, because if you square both sides, this would turn into cosine squared. I don't know how to write cosine squared theta in terms of x's and y's, so that's just not a good choice. The slick move here, as you can see I've done in green, I just multiply both sides by r. Right? It's a different way to make r squared show up on the left. And now this is just x. Clever. Again, I didn't think of that. Somebody thought of that and showed me. Right? Probably they didn't think of it either. Probably someone showed them. Right? Now I'm showing you. So anyway, there's various different tricks. By the way, I think it's worth pointing out that you'll notice that I completed the square on the left side of the equation there. Completed the square so that will turn into a perfect square, which of course we like. A lot of students are either never learned how to complete the square in high school, or maybe were told but didn't do it, or learned it but then forgot it, or whatever the case may be. High schools seem to have decided long ago to stop teaching students how to complete the square. This is outrageous. Completing the square is very useful. This is a nice example of it, right? So make sure you're good with completing the square. If you aren't, I'm sure there's a million online resources. If you don't find any online resources you like, come on into office hours. I'll show you how I do them. It's just a point of view, but I'm happy to help. But anyway, one way or the other, make sure you can do that. And then let's see here. This last one, and then I guess we'll have to call it a day. You'll notice I expanded this square before I started plugging in conversion formulas. And the reason why was so that I would see an x squared plus y squared explicitly and then I could just write that down immediately as R squared. The alternative is you start plugging the trig in at the very beginning, and then you have just more trig to wade through. So every so often, that's a convenient little shortcut. Okay. Good place to draw the line. Y'all have a great weekend. See you on Monday.